Corey Adams. I'm a computational scientist here in the Argonne Leadership Computing Facility. My own background is in high energy physics. I come from the world of neutrino physics. And I joined ALCF about 5.5 years ago, working in the data science and AI group. Today, we're going to talk about advanced neural network concepts, and specifically, this is going to focus on convolutional neural networks. I don't want to leave you with the impression that everything in modern neural networks is from convolutional neural networks. So if you navigate to the training page GitHub, I've put on a couple review papers here about different things from advanced neural networks as they're applied to science. Here at ALCF, we really focus on science applications and less on industry applications. So for example, there's a review paper on machine learning applications to material sciences. This is a paper on how to apply physics into your machine learning. That's an area of research that I'm also active in. How do you make a neural network work with physics constraints? And then another one specifically on the physical sciences, so a little bit more focused on practical experimental applications. And just to give you some context of what type of work we'll look at today with convolutional neural networks, here's a picture from a paper from 2019 that I'm a co-author on, actually. This is applying a convolutional neural network to real data from the neutrino physics experiment at Fermilab, where it was segmenting into different classes, 2 types of high energy particle. And the details aren't super important, but you can see that the yellow tracks are all very straight lines, and these lighter blue things are much more fuzzy. And this was the separation we were looking for. And the reference for this image is here below if you want. In today's content, we're going to focus on one notebook, but there's a second notebook prepared if you want to dive deeper and learn a little bit more. So we're going to mostly focus on this first notebook, 01_convolutional networks. If you are interested in this topic and you want to learn more about how this might connect to the rest of the class, there's a second notebook that you can look into. It takes longer to converge the model in this second notebook than we have time for today in class. So we're not going to really touch on it, but you're welcome to look into it on your own. There's no homework on it or anything like that. It's purely extra. Okay, so everybody who is going to follow along live, feel free to open up this notebook, ConvNetworks. You can run this on the ALCF systems. I'm running on Polaris in a Jupyter notebook. You can use our Jupyter Hub to run this, and you can also run this on Colab if you need to. There's one section on this that might give you an error on Colab. I'll talk about that when we get there, but it's not a super important part. Okay. So to give you some context on convolutional neural networks, if you've looked into the history of artificial intelligence over the last decade, you came across this ImageNet competition. The full name was the ImageNet Visual Recognition competition. It ran from about 2010 onward. And that was a big data set collected in the first decade of the 2000s that had a bunch of different classes. I believe there were 1,000 classes. And there are things like cars, people, airplanes, horses, etc., everyday objects, manually labeled, what I assume is great expense. And then the competition was train your best artificial neural network, or whatever model you want to use. It doesn't have to be an artificial neural network, and classify the objects. And over time, during this competition with this massive data set, people submitted better and better networks. 2012 was the first year that a convolutional neural network won the competition. And convolutional neural networks have been around since the 80s, actually. And some of the data sets we saw previously from Bethany were used in the earliest convolutional neural networks. They really blew this competition open with about a 10% accuracy improvement in 1 year, which was unprecedented so far. And that one was called Alex. And if you look up that publication, it has something like 100,000 citations. It's a sort of wildly influential paper and really launched the modern era of artificial intelligence. So we're going to talk about convolutional neural networks today. You can see on this plot that I'm looking at, this red line across, 5% error rate is the human error rate. There's lots of stuff if you want to Google about how that's actually calculated. If it surprises you that humans are getting some of these classifications wrong, you should look up into how the human error rate is calculated, and you can take some of these image challenges yourself and see that, yeah, these questions can be hard. The model we'll look at today, though, is roughly based on the 2015 winner. So the first network to beat human performance at this image recognition test. Okay, so again, we're going to use PyTorch. And we're going to start today just by talking about some of the building blocks of convolutional neural networks. So I'm going through these cells, so far just importing things. And then cell 3 loads this image, which should be on the GitHub folder, ALCF staff. It will load. You'll see this image. This is a staff photo from actually pre-COVID days. The machine in the picture is Mirror. It doesn't even exist anymore. This is where Aurora was built. The guy with the beard in the front is our director, and the guy in the back in the curly blonde hair towards the right side is me. We're going to use this image to demo some applications of layers of convolutional neural networks. Let's start with the first building block of a convolutional neural network, and that's the convolution itself. Convolutions are a mathematical operation. If you've taken anything in calculus or applied math or anything like that, you'll have recognized and seen convolutions. They've been used in many different areas. In neural networks, these are discrete convolutions. So that means that it's not a continuum, but a matrix type shape, in this case, particularly an image. And a convolution is just a set of weights. They're learnable for networks, but they don't have to be if you want to do convolutions for some other application. But you take some set of weights and you apply them to the image in a moving window fashion. So this image down here with the blue and the sort of light green squares is an application of a convolution. The dark shaded blue squares on the bottom are a location in the input image in blue where a convolution could be applied. And it's a 3x3 convolution, so it takes a 3x3 window, multiplies each pixel by a unique weight, so it has a 3x3 set of weights, adds them all together, and that's your output pixel in the top left. And then in this image, the convolution would step to the right one row of pixels and do the next 3x3 set. And once it hits the end of the image, it loops back around one pixel lower and goes through again. And to give you a sense of what convolutions look like, here's a convolution applied to our ALCF image. This is a convolution, and I'm applying it with this torch function package. If you're not familiar with this, that's okay. It's a different way to do neural network applications. Here I give it the input image, which I've converted to a PyTorch tensor from this Python image object. I reshape it. So the images in convolutional neural networks are typically shaped with the shape of batch size by some number of channels. I'll talk about that, and then it's by width, height, or sometimes height, width. And the number of channels is typically in an image red, green, blue, so 3 channels. But in a convolutional neural network, we actually generalize that and then dramatically increase the number of channels and think of it as a different way to encode spatial information across an image in a way that we can combine downstream into higher level objects. Okay, so I reshape this to have a number of channels of 3 and a batch size of 1. And then I apply this convolution down here, which is 3x3 for the filter size. I'm sorry, for the inputs, the number of input channels is 3, red, green, blue. Number of output channels, I use 3 again, red, green, blue, to make it visualizable. And then I did a 15x15 convolution. And you see in the bottom, it's basically applying noise to the image and really smearing it out. And if you adjust this, for example, and make this 15x1 convolution, it only smears out along one axis instead of 2. And you can even do a 1x1 convolution, which is just multiplying every pixel by some sort of scale. So this has no smearing at all, it's just changed the scale. The next important piece of a convolutional neural network is called normalization. Normalization came around in about 2015-ish. And there's a number of different types that are used now. This is a nice image from a summary paper on normalizations. But the main point in a normalization layer is that as you're training a neural network and you're taking the outputs from one layer and feeding it into the inputs of the next layer, as you update the layers, the total scale of the outputs of one layer are moving. And so the next layer down is always working with a moving target. It takes a lot longer to train that. You have to use a lot lower learning rate because it becomes unstable. Batch normalization is a technique that took the outputs from one layer and just normalized them to some sort of standard and before feeding them into the next layer. And it became a learnable layer where it keeps track of the mean variance. But doing this allowed significantly larger learning rates in training a neural network. And you can see in this graph on the bottom, this is from the original batch norm paper, and the link is right here below the image. The baseline steps to reach the inception model, which is what they were comparing against. It's an old model. 30 million steps. In the batch norm, they were doing it in single million number of steps. So multiple times faster in training convergence, and they even beat the final results. The normalizations that are really popular these days are not batch norm, but layer norm. The way you can read these images, these cubes on the top, is it's describing for you an image where n is the batch size, so some number of images per batch. C is the channels, so that could be red, green, blue. Here there's 6 channels in these 6 by 6 by 6 cubes. And then HW is the height and width axis. And you can imagine just taking that 2D image and compressing it into 1D. That's H times W long. Batch norm will look at a single channel and normalize over the whole batch and the whole height and width. Whereas layer norm, a really popular one these days, does it on the other axis. So it ignores the number of batches and will normalize over the entire image on the entire set of channels. And instance norm is the opposite of both of those, where you normalize just over a single channel and a single image at a time. So you look at the entire XY dimension of the image and you just pick one channel to normalize at a time. And then this other one is somewhere in between, which gives you a little more stability like layer norm and batch norm, but a little bit more fine granularity with instance norm. We're going to look at layer norm today and use that in all of our examples, because that's what's used in many of the transformer models today, which we'll get to in the next session. And particularly for layer norm in transformers and other generative AI, the number of batches you feed in at a time could be low. And layer norm is much more stable with a low n here along this n-axis. Okay, so to show you normalization, I'm going to apply it to the same image, this ALCF staff photo. If you see how it came out on mine, I applied just a regular normalization, so it set the mean and variance to standard values. The sharpness of the image is completely maintained, and the colors in the image are completely different. And that's because it's taken the values in the channels, the RGB, and completely adjusted their relative scales, which changes the way the computer is drawing the image on our screen. Okay, one of the last critical pieces of convolutional neural networks is this downsampling operation. And in some layers or some models, there's also a corresponding upsampling. One of the things that makes convolutional neural networks special is that they have what can be called an inductive bias. When you apply a convolution, and you look at, say, a 3x3 or a 4x4 or a 5x5 neighborhood of an image, you're forcing your network to learn local features, where since your filter is inherently small, it can learn a local feature and detect it in one area of the image. And it can learn the same feature or a different one in a different area of the image, but it's hard to bring that information together. As you go deeper and deeper into your network, the receptive field of the filters, which is just talking about for any given output pixel, what are the input pixels that contributed? That field grows as you apply convolutions, but only as the size of the network gets deeper. So twice as many layers makes it twice as big. And to cover a whole image, you might have to actually get quite a deep network. Pooling is a method that works to change effectively what the meaning of local is. So since your convolutions have this inductive bias, they're forced to look at local features. If you bring further apart features closer together, you can still learn the convolution. The most common downsampling operation you'll see is something like a 2x2 pooling. That can look like a max pooling, which on this left is where you divide your image into 2x2 regions and you just take the maximum value for each region. Or there's average pooling, which is exactly what you think. In the same 2x2 region, you take the average of all the numbers as the output value of the pixels. Most of today's modern neural networks actually use convolutional pooling, which takes a 2x2 convolutional filter and applies it not every pixel, but every other pixel. So that's called a stride. So the convolution moves in steps of 2x2, the same size as its kernel size, and that will produce an image 2 times smaller. And again here, you can run max pool, for example, on our ALCF staff photo, and you get this granular image. It is now half the resolution that it was before, which you can see based on how the image has turned out. And we've also lost some of the smaller features because I applied the max pooling instead of the average pooling. So if you go back and apply the average pooling, you will probably find the image from a distance looks the same, even if it has half the resolution. And it's not until you zoom in you start to see the loss of features. Okay. Another really important piece of convolutional neural networks, kind of the last piece of the puzzle, are these residual connections. The reference here, deep residual learning for image recognition, is pointing to the 2015 paper about the network that won the ImageNet competition, the very first year that computers beat people. So if you read just one paper about convolutional neural networks, I highly recommend you make it this one. One of the challenges that neural networks were facing in the ImageNet days was that as they went deeper and deeper in terms of the number of layers stacking together, they found that the performance of their networks got worse and worse. And what that means is they took the output of one convolutional layer, plugged it into as the input to the next convolutional layer, and they compared, for example, doing that 18 times on this graph on the left versus 34 times. So 18 is teal, 34 is red, and this plot of error percent, where lower is better, showed that the 18-layer network with less parameters was beating the 34-layer network with more parameters that in principle should be able to learn better. The reason for this is a problem known kind of as the vanishing gradients problem. And there's a couple other subtleties that go into this whole issue. But essentially, if you think about this, the backpropagation algorithm used to train neural networks starts to apply the chain rule more and more and more as you go further and further and further back in your network. And the value of your updates starts to get lower and lower and lower at the earliest layers of your network. So the 2-layer network, it's not a big issue. The 3-layer network, still not a big issue, but you can imagine every time you add a layer to your network, the scale of the gradients in your first layer is going to decrease because of this backpropagation chain rule. Residual networks solve this with the introduction of what they call skip connections. And that's what's in this picture, figure 2 here, residual learning. The idea was, instead of just applying convolutions sequentially, you introduce a shortcut connection every some number of layers. So you take input X coming up the top, it splits off into 2 paths. In the first path, it goes through a weight layer. ReLU here means rectified linear unit. This is a nonlinear activation. You go through another weight layer, and then you add it back to the original inputs. So instead of asking your neural network in this layer to learn a function of X, you ask it to learn a residual F x, the output equals x plus some residual f of x. And the gradient of this whole thing equals 1, which is the gradient of x, plus the derivative of f of x. And that helps you have a shortcut path for your gradients going deeper into the network. When they did this, they found that the 34-layer network on the right could suddenly beat the 18-layer network still on the right. And they found a pretty good improvement in the training of their models. Okay, so that is a high-level summary of the building blocks of the convolutional neural networks. In today's session, for the next half hour or so, we're going to talk about building a convolutional neural network ourselves and running it on a data set. If there's anyone who has questions about the building blocks, feel free to put them in the chat and we can stop and answer them really quick. So today's work, building a convolutional neural network, it's going to be built based on this paper here. If you follow it, it will take you to something called ConvNet. This is a paper from 2022. It's a fairly recent paper talking about what are the differences between residual networks and, say, transformer visual networks that are in the world today based on large language models. And what are the things that transformers have done that could be applied back to, say, a residual network? And they found that if they took all the advancements in transformers and brought them back to residual convolutional neural networks, the convolutional neural networks are actually competitive and can beat in many image tasks the transformers. So we're going to base our model today off of the networks they use in this paper. And the data set we're going to use here is CIFAR10. This is slightly harder than MNIST. If you haven't heard of CIFAR10, I'll show you some images here, just to walk you through something different here compared to last week. So I set the download to false if you're on Polaris, by the way, and I pointed it to a copy I have already downloaded. If you're running on Google Colab, you'll want to change download to true, and you can change root to something like data. And that will work for you on Google Colab. Okay, so CIFAR10, the images are slightly bigger than MNIST. Instead of 28 by 28, 32 by 32. That's not really a groundbreaking change. And as well, there are color images instead of grayscale for MNIST, which is just 0 or 1 for each pixel. These have an RGB value. And I'm applying some transformations here on the fly. So this is something I don't think we talked about yet, at least not in detail in this course. Many models are trained with a technique called image augmentation. And what that means is if you take an image, like a picture of a horse, it's labeled horse is horse, but if you flip the picture around and you mirror it, it's still a horse. So to you, to your eyes, that doesn't change the image in particular, but you do notice, of course, it's flipped. To a computer, that can make a big difference. And without things like image augmentation, if you train neural network, it may recognize the images of the horse pointing to the right. That's all that's in your data set. And the horse pointing to the left, it might actually not work. So image augmentation is a technique to enhance your training data set by introducing these flips on the fly. So I have a couple here, and there's many more. And you should check out this package, Torch Vision, if you want to learn more about what's available. So my set of image augmentations is this list here, and I put these together with this Torch Vision transforms.compose functionality, which is basically saying do all of these in a row. So I take the image, I convert it to a torch tensor. I do a random horizontal flip, so that would flip it left to right, but not always, it's random. I do a random resized crop. So what that means is I take some fraction of the image between, say, 85 to 100% of it, and I crop the image down to that region, and then stretch out what has been cropped to fit the original size. Go back up to a size of 32. And last is a color jitter, where that's just adding some jitter and noise to the input image in terms of its color scale. If you're working with real life photographs, this can be really useful because this can help you adjust for things like light saturation and exposure times, or any differences between cameras. If you're working with science data, this can sometimes be not as useful. So I haven't seen color jitter as much as I see things like random flipping, crop and resize in actual science data sets. In the test data set, I don't apply these transformations. I just let the test data set be what it is, because that's what we'll use to measure the performance of the network. And the augmentation can change those results. For this work today, I've set the batch size to 128. Like MNIST from last week, CIFAR 10 has 60,000 images. So batch size of 128 is a pretty reasonable size for this data set. If you find that you're working on Colab or maybe your laptop locally and this is taking too long to run, you can adjust this. On Polaris, you'll find that this runs fairly quickly. Okay. Last, I put these data sets into the PyTorch data loader, and I introduced the shuffle and num workers values to help speed up training for num workers and to randomly shuffle a data set for each key training. Okay, to visualize the images, we can use matplotlib again. I pull one at random from the data loader, and I visualize it here like this. And if you just click through this, rerun it, you'll see many different images coming up. Here's one that's at least fairly recognizable as an airplane. Okay, one other piece before we get to the network. If you look at the PyTorch documentation about using data loaders, they suggest doing something like this. This is a really useful tool where we're taking our data loader and wrapping it. Where this wrapped data loader is applying some function, which is this one pre-process here. And all it does is take the input image, make sure it's the right shape, put it to the device. Where the device is CUDA, the torch has CUDA, and otherwise it stays on the CPU. So this whole section of text here just takes our images and puts them on the GPU for us. Okay. Let's get into the details of the convolutional neural network. So in a convolutional neural network, typically you have a series of convolutions that you apply. So you do some initial convolution, and I'm skipping down to this classifier here for a second. You do some initial convolution, and then you apply a series of convolutional blocks and downsampling until you finally get to some readout of the network's output. So to walk through this in detail, I take an initial convolution here with a kernel size of 1 and a stride of 1. What that means is it's going to look at every input channel, RGB, with 3 channels. Then it will output for every pixel, whatever I set this parameter to, and initial filters. And that is a parameter of the model I've defined here, in initial filters. And kernel size of 1 and stride of 1 means look only at individual pixels. If you change this for bigger images to something like 4 by 4, suddenly this is going to look a lot like tokenization for large language models applied to vision models. But we'll stick with 1 by 1 here today. I keep track of the shape here because we need it as input to the layer norm layer. And all of the layers here, by the way, are not the functional networks, the functional interface, but the torch.nl interface, where you can find all of these layers in the PyTorch API online. So I have an initial convolution and then a normalization right after that to help stabilize that training. And then there's some layer of blocks. I've defined a torch.sequential object here, which I call layers. And I'm just going to append the layers I want to run. And then I will call this object to apply them all in with it. I do this for another parameter of the input, n stages. So that's some number of convolutions in a downsample together. And then how many convolutional blocks per stage is the last input parameter to my classifier. So I just loop over the number of blocks per stage and I add to my layers widget this thing here, ConvNet block. Then this I'll come into in a second. Once I've done this number of blocks per stage of these convolutional layers, I add downsampling, And again, I've defined a downsampler class to make this a little bit easier to write in just one loop. And then each time I downsample, I'm doubling the number of filters for the neural network, which means that though the spatial resolution is going down by half in both dimensions, the number of channels goes up each time it downsamples. So that helps preserve some of the information in the network as the spatial information gets smaller. And finally, I have this last piece called head, which is just the readout of the network. And it's going to take the images, which have gone through substantial transformations at this point. It flattens them. It applies another normalization. And then there's just a linear layer to go from whatever the current number of filters is to the 10 classes that means the filter. And the actual application of the network is pretty straightforward here. You take your inputs, you put it through the stem, you take your output of that, put it through normalization, then X goes into the layers object, so that's going to apply the bulk of the network. I do an average pooling with the function interface, which just takes the final output shape, which is probably a spatial dimension of a few by a few, so 3 to 4 pixels per side, and it brings it down to just 1 pixel. An average over every image is every red, green, blue equivalent filter in the final image, and then apply the classification. Okay. To get into the meat of what these layers are doing, let's look first at the downsampling layer. It's pretty straightforward. I'm doing a convolutional downsampling. So I take the inputs here in the forward function, and I apply the normalization, and then they go into this downsample object. And that's all it is for the downsampling class. For the downsample object, again, it's just a convolution. And it's totally possible to take this and change it for max pooling, average pooling, and you'll get a different network with possibly different performance. And one thing to note is I've set in this downsample the kernel size and the stride to be the same value. So whatever I input up here, 2, for example, it will do a kernel size of size 2 with a stride of 2, or if I entered 1, it would be kernel size of 1 and a stride of 1. And the downsample factor of this class will be whatever this value is up here. So this will downsample it by 2 in both X and Y. Downsampling by 3, you could do by just changing this to 3. If you change it to 1, it actually wouldn't downsample at all, because downsampling of 1 is not downsampling. The other piece of the network here, this ConvNet block, is going to take the inputs and put them through something slightly more complicated. So let's walk through this. The first step it does is it takes the inputs and puts them through convolution 1. That's up here. It's again PyTorch convolution 2D. The input channels and the output channels for this are the same. So this is applying, not changing the size of the output image, but it does apply convolution to the image to produce a new output so it can learn more features from it, but it doesn't actually change the output sizes. And it uses a very large kernel compared to something like what the original resonant is. So 7 by 7 is quite large. The padding here, that's a parameter that's useful to know in terms of convolutional neural networks. When you apply a convolution and it's moving some filter across your inputs, if its convolution is any size bigger than 1, the output image will be smaller than the input image. One thing that has made this easier to manage is called padding, where you take your input image and you pad it, typically with zeros around the edges, to produce an output image that's more reasonable compared to your input image. So using the padding of same, I'll produce the same output image size as I get with the input image size. And PyTorch will take care of the math for you for how much to pad it along each axis. You can do it manually too. You can set integer numbers here, similar to your kernel size, for how much to pad. And there are other options for padding as well, like valid, which will produce an output image that's the same, that's only applying the convolution to non-zero input pixels, so it doesn't pad any pixels. After the convolution, the outputs of that go into a normalization and then another convolution. And the convolution down here, these ones based on the ConvNet architecture are actually one-by-one convolutions. So you can think of a one-by-one convolution as just looking at a single pixel at a time with the same network applied to every pixel. And this particular technique will take however many input channels, the green-blue equivalents. The first one learns 4 times that many in the output. So it has a very large output space to learn on. And the second convolution here maps that back down to the original size. And in between the two, when you apply it, you have a nonlinear activation. So this one, this is Gaussian error linear unit, is commonly used in transformers, which is why it's used here. But any nonlinear activation principle can work. And as part of the residual network magic, we have to then take the output from this final convolution layer and add it to the inputs. So we return X plus inputs. Okay, that was a lot of detail about convolutional neural networks in practice. I'm going to hit Shift Enter here so I can show you what the model looks like. But please, if there's questions, go ahead and ask. Okay. So I initialized an instance of the classifier here. And if you don't recall, I'll remind you, the inputs to this class I created in Python were how many initial filters to use, how many times to apply convolutions in a downsample, and how many convolutions per stage. So here, if I do 64 initial filters, 4 times convolutions and downsamples, and 2 blocks per stage, it made some instance of a model. And I use this torch info summary function to print it out. And if you're running on Colab, I'm not sure if torch info is installed by default there, so you might have an issue with this particular block of code, but it's not actually essential to the rest of the notebook. Looking at the output of the neural network's layers, you can see the whole thing here. So this layer here is the initial piece of the network, and so it takes the convolution, the input images, and produces 64 output filters. You see that here. All of these shapes are batch size, comma, number of output filters, comma, XY. So it's still 32 by 32. And then it does a normalization, and then it goes into these layers, which are defined in this sequential object here. I did 4 sets of layers, so we should see downsample show up 3 times. So 1, 2, 3, and then there's no downsampling applied on the last stage. So that's here. We skip it if it's the last layer, just because there's going to be an average pooling before reading out the network, and so downsampling is not the same. Each time it downsamples here, for example, the input to the downsampler layer here is the output of the previous layer with 64 filters, 32 by 32 size. When it downsamples, you can see it jump from 64 to 128 filters and 16 by 16 spatial size. And you'll see that pattern repeated each time it downsamples. And in the individual convolution layers, you can see the pattern of, this is the large input convolution with 7 by 7 filters, for example, and then it goes up by a factor of 4 in the number of channels and back down again to 120. And you can play around with this on your own. You can make this much larger. So if I do 512 instead of 64, the total number of parameters in my network might go up. So from 7 million, let's see what it gives me. Now my network has nearly 500 million parameters. Certainly for CIFAR 10, this is overkill. but you do see convolutional neural networks with this size of parameters. And the memory used in the network is quoted here as 16 gigabytes. So this can actually start to add up very quickly if your batch size or image resolution increases, or if your number of parameters gets very large. And if you make this small again, down to 16, now we have just 600,000 parameters in our neural network, and a much smaller half gigabyte of memory usage for the forward backward things. For the rest of this notebook, I encourage you to pick a number here, some number of filters, some depth, some number of convolutions to train your network and see how it comes out. We'll train these live in a few minutes, and you can track, compared to your peers, what the models are doing. And part of the homework will be changing these parameters or other things in the training to see if you can beat the training that I'll show today. So I'll try 32. Okay, so now that we have convolutional neural network, mine ended up with 2 million parameters. I need a way to both train and evaluate the performance of the network. So I'll focus here on the train function first. This should look similar to last week's train function, but I'll walk through it again. It is a function that takes in a data loader, some model, some way to compute a loss, as well as an optimizer. And this piece here is just for fun, basically, a progress bar. Once you call this function and provide all these arguments, it will run, it puts the model in the training mode, and then it will loop through the data loader. And because PyTorch data loaders know how many images in the data set, this will stop automatically, then goes through all of them. Compute the prediction for the model. So I just call the model on X, the input data, and then I compare the model's output to the predictions. So to the truth label. So the loss function compares the prediction to Y. And this is the same loss in the end. That's this cross entropy loss that you were using last week for a much simpler model. This loss function is one of the most important loss functions in machine learning. This step calculates gradients. So the loss is what we want to optimize and make as small as possible. So we call loss.backwards. And the optimizer takes one step with those gradients, and then we reset the gradients back to 0. And this progress bar we call update, just so it will tell us how far along it's moved in the training. The evaluate function is very similar, except we put the model into the evaluate mode, and we don't have to call backwards. So we still make the prediction from the data loader. We predict the classes from the model. We still compute the loss, but we don't call backwards, and we're just adding it to a running total of the loss, which gets normalized down here. So this is just computing the mean over the whole data set, the whole validation data set. Like last week, we have the same loss function, but a different optimizer. I believe last week we used stochastic gradient percent. This week is an optimizer called Atom W. There are many optimizers out there. I'll show you SGD here. And then I'll have you change to Atom and retry this in a second. So I started running this. I have to evaluate these functions. There we go. So this is just running 30 epochs, training 1 epoch. Don't worry too much about the details of this progress bar. That's just what's making it show up in blue and green here. On Polaris, it's taking about 30 seconds to do 1 epoch plus the validation. And we see the training loss start to decrease. So after the first epoch, the training loss was about 2. Validation loss was about 2. But second epoch, well, that was 0. But like epoch 1, it's gone down a little bit. Epoch 2, a little further, and it's still going. So at this point, I'd like to take a moment for some interactive, try it at home stuff. So I'd like everybody running this online, change this optimizer, if you like, to Atom, or AtomW or any other optimizer you like, and try running this training loop for 30 epochs. It will take us about 5 or 10 minutes to run. I'm happy to answer questions while everybody's running the code. And you can compare your performance with mine at the end. And then for the homework, you can change more things and resubmit with maybe a different work or a different optimizer or whatever you want to try. And then for the homework, you'll just have to submit what was your validation and training loss and accuracy and what you changed to the mark. Okay, so I'm going to leave mine going here on the screen for the 30 epochs. I'll keep it updated. And then can't offer stickers to anyone who beats me because we're virtual, but I hope that your network performs better.
Corey, we have one question in the chat from Alfred who asked, when the codes are run on Polaris, do they automatically run on GPUs or CPUs?
Great question. It depends on what codes you're running, but with something like PyTorch and TensorFlow, it's pretty easy to make them automatically use GPUs, but it's not guaranteed. And that's why I included that wrapped data loader above to make sure it was always moving the data to the GPU. So this is moving the data here. This torch.to function to the CUDA device. And I called this function here model.to, which moves the whole model to the GPU device. Once you've done that, and your data is on the GPU and your model on the GPU, it will automatically run on the GPU. I see someone asking in Slack which kernel. You should use the Conda 2023-10-04 kernel. That's the one looking question. And you're on Curates. Top 21. My loss is stabilized to about 48% accuracy. If you recall, there's 10 classes, so 10% is random guessing. So it's beating random guessing. It's nowhere near state of the art. Part of that is the optimizer. I'm interested to see if people want to post in either Slack or the Zoom chat what accuracy their models have reached with the validation data set. So,
there are also some questions in Slack about scientific CNNs, if you want them now.
Yeah, I'd be happy to have them. I didn't see them.
Question about what the channels would be for a scientific data set, if not, pixel color channels.
Yeah. I scrolled down and see the image of all the questions now. So for the data I showed before, say from that microboom data set, that was read off of electronic sensors that had just one value in DAQ. So they read the value of current at a particular time, and that was it. So the input data there is actually one channel instead of 3. That's not super uncommon. You see that a lot in many digital devices that they have just one value read out. Astronomy pictures, if I understand correctly, the ones that are color or artificial color, and they typically just read in grayscale or have multiple exposures. So if you have multiple exposures of the same galaxy, you can combine those into RGB or more images. And if you don't, you can just use one channel and quickly have your network run to pick that up to 16, 32, or more channels. For that, answer that question. see one in Zoom too. The training validation data sets are different from the testing data set. Yes, in this case they are. The training validation data set is a split of the 60,000 images in the SIP-R10 data set. I'll show you where to do that. Sorry, it's an 80-20 split. Sorry, not 60, an 80-20 split. I take the training data and I use this torch.data.random split function, which will randomly split into 80% training, 20% validation. The testing, if you've noticed, I don't actually use in this notebook. So I encourage you to try your model on a test data set once it's done training. Yeah, I see another question on Slack. Corey said that CNNs are still performing relatively well to vision transformers. Yes, I think that they are, but something like the original ResNet might not be. Some of the things that transformers have learned is when using a vision transformer on computer science or computer vision tasks, they can often take advantage of pre-training with large data sets and do really well. In a scientific context, I have found that the scientific data often doesn't look like the pre-training data sets. So my data sets from neutrino physics are in 3 dimensions and they're sparse, and there's no pictures of cats, dogs, airplanes, or horses that we've seen yet, at least in our data. And so the pre-training may or may not be as applicable, and some of the inductive biases you gain from convolutional neural networks will play a role for computer vision tasks of particle science. On top of that, that paper I referenced was comparing and what we built the model off of in this class. Let me find it. Here. If you follow this link, you can read this paper. They compare to vision transformers and find that if you use the same tasks, the same tools the vision transformers are using, you can reach the same accuracies with them. And I'm sure someone could leapfrog this and say, if you use the same things that the convolutional networks are doing in the vision transformers, you can make them even better still. So as it goes currently, both fields are still evolving, and I would say both techniques still have a lot of applicability over vision tasks. With the other questions, if we had only one channel, then there isn't a concept of layer norm. Does anyone use both batch and layer norm together? Channel norm is based on all the numbers in the batches. Certainly you could do that. If you had only one channel, an instance norm technique might be best. I haven't seen many networks that will take one channel all the way through the entire network. So typically it grows quite quickly to something that is more than one, and layer norm becomes useful. Batch norm is still useful if you have batch sizes that are large. So if your local batch size is relatively large, you're meaning tens or more, so 64, 128, you can get great performance with batch norm too. Layer norm becomes particularly useful when your local batch size is small. I'm going to check on the number. People post more questions. Okay, mine has finished. 47.9%. Anyone else who's finished? Post your numbers in the chat, and hopefully we keep this one. For the homework, you can easily get above 70% with just a couple changes, and they're not complicated changes. Good job, 76%. Okay, just as a final thought here before we wrap up our science speaker, I'll say some things about the homework. I put some text here. The convolutional neural network I trained did not really overfit 47 versus 48.5, 48 versus 48.5 accuracy. Some of the ones that saw Nathan's in the chat was overfit pretty badly. So training accuracy at 94% versus validation accuracy at 76%. Still, the validation accuracy keeps mind, so it's an improvement. There are ways to address that, and if you're interested in that topic, the second notebook, which we're not going to cover live here today, gets into some more modern research on how to handle that. It's different from just data augmentation. But in the meantime, the homework for this week is to retrain this model, but try again with a different architecture. So I picked some architecture up here. I changed these parameters, 32, 4, 2. Change them however you like. You can change the initial patchify layer. You could add another hyperparameter. You could add regularization such as dropout for the final layer. You can change the optimizer. I used SGD here. It's add on W on the repository. You can try something else. Change the bat size. Whatever you want to do, and it doesn't necessarily need to beat it. For the homework, to get a full score, I'd like to see what the training looked like. You can make a table with the loss in accuracy for training and validation, or you can plot them. It's easy enough to do. For all the epochs you train, so try to go for 30 because it only takes a few minutes. And also just a few sentences about what you changed in the network and why you think it made a difference. So maybe what you were expecting, maybe what it turned out to show. This type of exercise can often be a little bit magical type of parameter tuning, and you don't always get the results that you think you'll get. But it's good to try things, and you can gain some intuition over time about if you change something in a network, how will it change the output? For example, adding more to this network won't do much. The first thing I need to do is change my optimizer here to include the score. I know that based on experience with both SGD and emergent-based optimizers. So that's the homework. Paige, I'm going to turn it back to you. I will stick around and answer more questions in the Slack chat.
All right. So I see that our speaker has arrived. So for our science speaker today, we have Katerina Vriza. Katerina is, excuse me, as I pull things up. Katerina is incoming staff scientist at the Center for Nanoscale Materials at Argonne National Lab. The CNM is one of our many user facilities, just like the Argonne Leadership Computing Facility. Her focus is using AI ML to extract scientific data from literature and using that data and machine learning and robotics for the design and synthesis of polymer materials. She works on an autonomous materials synthesis for a robot called Polybot. Katerina is also the current lead developer for EXSCLAIM, which is a code that extracts and curates labeled electron microscopy datasets using AI. So I'll hand things over to Katerina and we'll go from there.
Yeah, thank you very much. I'm Katerina. I'm based at the Center of Nanoscale Materials. And today I'm going to give you a very high-level overview about the work we recently have finished, about how we can extract and process multimodal data from literature so that we can guide autonomous experiments in our lab and synthesize new materials. So nowadays, we just want to create like new materials, we want them to be sustainable, and we want to make them fast. But there are several challenges on that. So first of all, we have limited data that are in machine-readable format, especially in literature. So we have to manually create data and extract the information that are relevant to our materials. So we can develop automated data extraction tools and use language models for automate this extraction. We also have experiments that are based both on trial and error, and so that we have like a reproducibility. So for that reasons, we need machine learning data-driven experimentation and to perform high-throughput experiments, and especially this is the usefulness of autonomous laboratories. So today I'm going to present three main tools that we have developed to help us guide our experiments and accelerate the synthesis of polymers. So the one tool is called EXSCLAIM, so can easily extract automatically images and caption pairs from literature. So we can train multimodal models with that. Also Plug to Spectra, which can digitalize some spectral images, and then we can calculate several properties that might derive from this spectra. And then also I'm going to introduce our autonomous laboratory Polybot when we can perform some of our experiments. So first of all, the importance, why we do this research. So we are aiming to develop some new sustainable polymers that can be used, for instance, for smart windows and energy savings. So to synthesize them, we need to find the correct recipes, what kind of monomers to combine to be able to get the correct formulation to synthesize a thin film material that can have controlled color. So our search space looks like that. We need to select among different monomers, we need to select the ratio, and then we also need to characterize them using the absorption spectra so that we can know, based on that, what is the color of the polymer we synthesized, and also what is the electrical property, for instance, the band gap. That is important. So we need molecular structure and absorption spectra together with their percentage. So to do that, we followed like a three-steps approach. So first of all, we extracted and analyzed the data from existing literature, so to learn what has been done in this field so far. Then we use this data to train machine learning models, and then we establish a robotic network so that we can run our experiments autonomously, and they will be guided from our machine learning model, which is trained on literature data. So to create a database that we need from literature, first of all, we can have a target material in mind, for instance, to query several journals about electrochromic polymers, which are of interest, and then based on that, extract all the images and related keywords that describe them. So the type of image that we care about in our research is absorption spectra and structure image data. So by creating these image text pairs, and we can have a lookup table, then we can only separate these images that are appropriate for our workflow. So I'll explain a bit more how this EXSCLAIM tool look like. So this is how a page of a journal looks like. So we have lots of images, the one together with the other, and then a full caption describing the full image. So by using EXSCLAIM, which is paired with ChatGPT, we can read the full caption and understand each subcaption, and then assign each subcaption to each subfigure. So by doing this process, we end up having a huge data set with all the image and text pairs. So all the images are described from their keywords. And now, for instance, we can know that this is an absorption spectra image. Another image is maybe a molecular structure image. So by doing that, we screened several images from electronic polymer papers, and then we only kept those that are related to molecular structure or absorption spectra, which is where actually the most the absorption spectra is the image that you mostly found in this type of research, because this is the method to characterize this type of materials. So by creating a database with all these image and text pairs, we can query it and then just get out only the absorption spectra images that we are interested in. So by analyzing them and digitalize them, we can now have a value, like a color value based on its spectrum. So we can use that to train our machine learning model, which is basically uses some structural characterization for our monomers, some electronic characterization for our monomers, and their ratio. Then we train our machine learning model with citation-based, and then we can get as a multi-output the LAB values, which actually describe the correct color of our polymers. So by training this model on literature data, We tested several architectures, so compared it with several other models that can be used so far, which outperform them. And we also tested several several features. So either to include electronic features or just structural features like fingerprints. So we selected the fingerprint that works the best and the model that works the best, and then we use that as a guide for our autonomous experiment. So this is how our lab looks like. So we have the machine learning model that is trained on all this literature data. Then we transfer the data to this platform. We synthesize the material and then we characterize it. After we characterize it with the absorption spectra, we send the feedback again to our machine learning model and just do this loop as many times as required to reach our target. So I have a video, like a short video, how the experiment looks like. So how we transfer, so the machine learning model that's trained on this data is sending now the recipe to the robot. So the robot is doing the whole process. So transfer the solution, the reagents to the reactor, then it's kind of, yeah, I don't know if, yeah, usually, okay, I think, let's skip the video, yeah. So yeah, the process is actually, yeah, like this. So we send the recipe to the ChemSpeed. The ChemSpeed synthesizes the experiment, and then it sends a command to the UR5 arm to pick up the plate with experiments and move it to the instrument that will characterize it and measure the absorption spectra. And then this instrument will send feedback to the robot to pick up the plate and return back to the ChemSpeed and take a new recipe from the machine learning model to rerun the experiment. So this is how the data looks like. So if we want to synthesize, let's say, a polymer that has orange color, we can pick up which color we want, which kind of monomers we want to combine, and what type of recipe we want, either to have 2 or 3 monomers, and what is the ratio step. And then by doing the loops, this is what the user is selecting. And then by loop 1, loop 2, and loop 3, we can see that it's even closer and closer and closer to synthesize the polymer we're interested in. So at the end, we managed in 3 loops to find the material having exactly the color the user wanted, and then all the process was just guided from this machine learning model that was trained on literature data. So that was overview. So the video didn't play that well, but yeah, it's kind of showing how the whole robotic process is happening. So I'm happy to take any questions.
Thank you, Katerina. So anybody with any questions are welcome to drop them in the Zoom chat or on Slack. And I see someone's typing, but while they type, I think one question I have is sort of in this sort of space where you're taking literature, you're using AI, applying to and grabbing things out. Are there like significantly big challenges that you face or others face as they work on this sort of work?
So, I mean, I currently with all the development in GPT-4 especially, all the challenges we had before that, you know, the caption cannot be extracted that clearly, most of them have been overcome. So the only big challenge now is that you have to pay. So GPT-4 works pretty well, but then, you know, it's expensive, especially if you screen like 5,000 papers. Then, you know, it's pretty expensive. We need something open source that is as reliable as ChatGPT.
Interesting. Okay. A question from Nicholas. How is the data obtained or selected?
So we have a pool of papers that are related to electronic polymers. So it's the category of polymers we're interested in. So and then we just give this as feedback to EXSCLAIM. So it's a journal scrapping tool. So by giving all the journals there, then we just extract all the information. So we scrape all the text, we scrape all the images, we scrape all the captions, and then we can even separate all the figures to the subfigures and subcaptions.
Another question from Zoom. Ron asks, can you learn the reaction temperatures or catalysts to use?
Yes. I mean, it depends on how you query your AI assistant. So for instance, we have you set up your AI assistant, which is based on GPT-4, which is a very powerful model. And then you just write your prompt. You describe what kind of information you want to extract. So for instance, I'm interested to extract all the catalysts, the temperatures, the base that is used to the polymerization. So it's actually works pretty well in identifying which paragraph is related to the synthesis protocol and then get out all the information. But of course, you still need the user to check them, so to make sure that everything is correct.
Great. Another question, just generally, do you know if this technique is being used like broadly or like in other fields, that like scraping and then applying?
Yes, I think now there are lots of people doing that in several types of materials. So I think it's kind of they are testing now like even the vision models, so that you don't. Yeah, I recently read a paper that they use GPT-4 vision just to screen all the images one by one, and then identify which is the part that is the image and what the image is showing. So not even using, I mean, we use like data scrapping. So by taking all the HTMLs from the general pages.
Okay, cool, thank you. Another question from Zoom. Julian asks a very practical question. How do you load the robot with enough chemicals to synthesize any material the ML model comes up with?
So we predefine the synthesis parameters. For instance, we have here, we know which kind of monomers we feed our ChemSpeed robot. So the model is only allowed to give suggestions among these materials we have already there in the robot. So that's why we pre-select like, which materials we have. So you can't really give any suggestions. So you just select, rank which of these possibilities are the best around in the robot.
Another question, Trent asks, can you talk more on the application of ML in the robotic field?
Yeah, so I mean, the way we use it now is to extract the data, train machine learning models, and then use these machine learning models to guide robots. But I think it is, you know, it is much more broader. So how machine learning can be used with robotics? For instance, another application that we are very interested about is how we can incorporate like vision models to the robot. So to have the camera on the robot and then to check the space where the plate with the experiment is, and then so the robot can go and pick it up from there. So without need to give the coordinates to the robot, because if you move the robot, anytime you move it and you return it back, it might have some deviation on the position it will be parked. So we need very well like vision models, like multimodal models that can take photos of the space and then know where the material is so that we can pick it up and move it around. I think this is a very cool application in robotics.